Okay, so good morning, everyone. And now, in the second day of my talk, we will cover more about the models today. So, as we talked yesterday, we discussed the various machine learning pipeline phases. Like once we get the data, we will get rid of the data that okay, what type of data we actually required. Based on the type of data, we required our features. So, which features are really important to us or which are not, and what all are the algorithms we have covered over there. So we discussed a lot about these feature extraction, pre-processing of those features, and more about the how we can get the relevant and irrelevant reduction of the features from our feature set pool. So once if you thought about that, once we are done with the data extraction phase, data cleaning phase, feature extraction phase, feature selection phase. So till yesterday's lecture, we covered about all these four aspects till the feature extraction and selection. So after the selecting the relevant features, well, now we have a reduced feature set which is called as a f dash. This reduced feature set is now is actually this reduced feature set is going to be used by our this train model training or for the modeling perspective. So this modeling is actually most of the cases we are actually interested about the classification phase. So what all are the machine learning classification algorithms we have in our this modeling phase? So we have the logistic regression type of thing where we can deal with the continuous amount of data or the time series data. So in case we have that form of data set with us where we can have a continuous of the time series nature of the data, we can use the logistic regressions for our predictions. Next, we have a name-based classification. This name-based classification we will require when we need a more probabilistic model for our network, like for the text classifications and all these things. Decision tree, a very intuitive embedded feature wrapper class where we can get the hierarchy of our features, that which features are really important. Those features will come on the top, and while other features they keep on coming to the nodes of the decision trees, and this is on the basis of the entropies or the distribution of the nature, which is going to help us to find the most appropriate level of our data set. So this is more towards like in case we are going to identify a sample from our existing data set only, then we can take the help of this decision tree classification. Beyond this, we have some different machines like a support vector machine where we can use our binary classification problems, more specific when we have a hyperplane, and this hyperplane is going to divide the data set into two partitions, and we can say that okay, using a linear line, then we can use a linear regression or a linear kernel function, or a non-linear line for which we can take some non-linear kernel function within a SVM, and that can help us to partition the data in two classes, which is more realistic towards our binary classification problems. Then we have the random forest, which is a extension where we can get the decision trees type of thing. More number of trees we can take, and all these trees are actually not interconnected. They are taken independently, and then we are going to merge it. So these collection of all multiple trees is actually form the type of a forest where all the trees are aligned, and the collective results of all the trees is considered to be a part of our random forest. And the last one is our KNN algorithm, which is actually known as a lazy classifier, and it is found better with respect to some this naive-based decision trees, logistic regressions. So this has two powers. The first power is how many number of neighbors you want to consider on, and on the basis of that, this classifier is going to give you the most accurate predictions based on the neighborhood. And the second is this classifier is actually a multi-class you can be used for the multi-classification problems. So in case we have a more than two labels, then we can say that other classifiers is not going to help us a lot, while KNN has the power to consider this that aspects like in case of a multi-distribution of the classes labels, we can go for the K nearest neighbor classifier. Even then, if this classifier is considered as a lazy, and why lazy? Because it doesn't create any model for the future. Whenever in a runtime you will pass the test set, on the basis of the test set, at every iteration it will check all the data samples it has in a training. So that's why it is considered as a lazy, because it is not going to build any model for us that can be utilized in the future for making faster and a better prediction. So every time you will pass the test set, it will consider it. It will take consideration of all the training samples, and then only you are able to interlink with this test set. Beyond these classifiers in a machine learning, other models which are available with the machine learning is our unsupervised and the reinforcement learning. So in a unsupervised, we will go towards the segmentation, we will go towards the clustering part. So there we can use our k-means, fuzzy c-means algorithm. Somewhere we can use this SVD, singular value decomposition, so that it can decompose the images or the test sets into multiple different parts. So we can take care of that, and we will consider that this was a part of my segmentation of the clustering. So we have some association analysis like the a priori or the FP growth analysis. We have the hidden Markov models where we can check out that dynamically in a real-time environment, that we can check it out what is the probability of our futuristic events rather than focus only on the present state. So this is a different type of Markov model where we actually take care of the present state, and we are going to predict that what can be the probability of my next day or the next iteration or the next time stamp in our data analysis. So mostly it is going to be used in your stock market predictions, it is going to be used in our weather predictions. So where we have some hidden layers, we have the hidden associations, and then based on these hidden associations we can find it out that okay, in a long term, in a long run, what can be our possibilities. So this approach is mainly used in a stock markets, in a mutual funds analysis, like for a long duration, what amount of profit we can get in our stocks market. So these are the machine learning algorithms overall where we can apply our modeling. So beyond this, if you will check out this slide, then you will find out that nowhere I have used the neural network. Okay, so neural network is not going to be used, while neural, with the help of the neural network we can do the classification, we can do even the segmentation. Most of us have used the neural network for the segmentation as well, to divide the task into the two groups. So this neural network model is not considered here in this machine learning pipeline or the framework. Why? Because neural network is not a one term. It is actually a broader domain, which is considered mostly in a part of your AI pipelining. In case if you have a AI pipeline, you are working in a AI based systems, then you can tell, okay, now we have to introduce some neural networks in our model. So, going forward, I will talk about a lot on the neural networks. So, let's first discuss about this modeling parts. So, is there any of the shelf models we have? Like this model is the most perfect one. We cannot go ahead of any other model. We cannot try any other model because we have a model which can give us the best accuracy, best in class accuracy. And in case yes, if we have any such model, then we are not in a requirement of any new models in the market. So is there any off the shelf model we have for any specific problems? The second concern is about how we can incorporate the context or the prior into the model. Can we introduce or can we incorporate the context in which reference I am talking about with my data. So this second concern is mostly used in when we have a speech or when we have a text type of data analytics, that okay, in which context we are talking about this thing. So which type of model is the model is handling this context in, or the prior knowledge is available to the model. Next, a big question which is actually asked by many of us, like which is going to help us in our modeling part. It is a machine learning or it is a deep learning models. So we will talk about this phase as well, that which model is going to be used, machine learning and deep learning. Actually, nowadays the era is of deep learning, and most of us keep on hitting the deep learning models. But when I asked some authors that why only deep learning, why do why we are not working on the machine learning, so they have not the exact answers that why actually deep learning is required for our problem. So do we have experimented our data with the machine learning models? And yes, if we are unable to find some solution, relevant solution with the machine learning approaches, then yes, we can say that okay, now we can move towards the deep learning. But in case we have a data set and this data set is actually working fine with the machine learning algorithms, then why we actually require a deep learning, complex deep learning models which requires the GPUs and high dimensional systems. So we will talk about this deep learning architectures, deep learning phases as well, and then I will show you some of the works which I did in a machine learning in every phases of these machine learnings, such that we can introduce some new aspects in a machine learning environment as well, not only on the deep learning. So let's start with this modeling. If you will check out the top model, training data, we have to load this data in our system. Then we have to do the pre-process. We have to extract some relevant features. Feature selection phase is now the optional one. We can use or we cannot use. So we have this feature extraction, and then we can move towards our model training. Using all the training data, my model is keeps on learning, learning, and learning. Once my model is learning is complete, now I will give us some new data. Most probably while doing experimentation, we will talk this in a form of the validation. We will talk this in a form of validation data. Once this validation data is being passed, it will again go for the pre-process feature extraction. And once after getting all the relevant features, our model which is learned previously, this will interact and we can find the instance that okay, what instance we want to give or my model want to give to my test sample, and that's how we can provide the label to my data set. While if you will check it out at the lower image, we have the deep learning model where we have the input layer, input neurons, and there are multiple hidden layers associated in between the input and the output. So this input class and output class, this is differentiated, this is partition, this is making exertion between the number of quite large number of hidden layers, and that's the these number of hidden layers or the length or the displacement between this input and the output layers is actually called the deepness of my model. So as much as deep as possible, you are actually working in a deep learning models actually. So these deep learning models, every layer, now input layer, the role of each and every layer is totally different, and it totally depends. It is not the heuristic or it is not the hit and try that how many layers I want. I need to place 10 hidden layers in between input and output and my model will become better. No, it totally depends. In once you are focus towards the designing of your neural network or this deep learning model from the scratch, then you have to think about it that how many neural network layers, intermediate hidden layers I must require for my application. And this is why this is so. because every layer has a specific role in our deep architecture. Like my input layer, this input layer role is to take the input, while the output layer, the role is to provide some labels to my output classes. So we have the class mappings at the output layer, we have the class mappings, these features on my input layer. And while these hidden layers, they keep on providing some aspects like suppose I want to do this face recognition example, then what I have to do, I have to pass one face as an input. I will extract some relevant features from this input image. Once all the features is been extracted, then what I will do, I will go towards my edges. First, horizontal edges, vertical edges, slant lines. I need to find all such type of edges. Then in a second layer, I will try to merge these layer or these edges, whatever I have found. So once these edges is going to merge, they will create some specifics like eyes. You can get the eyes. You can get curved lines are there, slant lines are there, you will join it, you will get some intermediate shapes. Then these intermediate shapes again in the third layer, again these intermediate shapes will going to join again, and that's how we can generate our complete architecture of the model. So the main crux of these deep learning models is you need to pass the input. You have to decide how many number of layers you want in your intermediate as an intermediate, and what output class you want to take check out. So but if you will compare these two models, machine learning and the deep learning, then you can find that okay, in a machine learning task there is a lot of complexities in a form that which feature extraction algorithm do we need, which feature extraction algorithm is actually required to us, and how many features we need to select. While in a deep neural networks, you are getting the ease of this all parameters. You need to simply pass the input as in a form of image. No feature extraction. You are not taking care of any features. Model will take care in on your behalf. So once you are done with this, you will move ahead. Then all the intermediate layers, they keep on extracting the relevant informations for you, and then at the last you can get the desired output at your end. So you in this is completely in a form of this black box. This input and the output is visible to you, but while these all hidden layers will become a black box, you simply pass the input and get the output. So now it seems yes, deep learning is much better as comparative to machine learning. Okay, let's check out the differences between these ML and DL. Factors, data requirement. Deep learning actually requires a very large amount of data while training. We cannot apply a deep learning models and say that my model is perfectly workable in case we have a very small number of images. While machine learning can train on even on the lesser data, if you have a limited data, then machine learning is most feasible for your application. While the accuracy, yes, deep learning provides a high accuracy, machine learning gives a lesser accuracy on respect ki how many what type of learning you have done with your model. But comparatively for the same problem, same domain, same data set, if you will compare the accuracies, yes, deep learning will provide a much better accuracy as compared to machine learning. But why it is so? Because in a machine learning, once you pass the image, you are actually taking care of that image with respect to the your predefined features. In case your features are really good, then your machine learning will also provide a very good accuracy. But which features we need to extract is totally heuristic. That's why we our deep models, which are actually taking care of all the original pixels of my image, will provide a better accuracy as comparative to machine learning. Training time, deep learning models really take a lot of times, even up to 1 days, 2 days. If your data set is large and your deep model is quite complex, then it will take up to 2 or 3 days as well. While machine learning, it will take a very less amount of time. Learning is quite easy. faster and you can get the output in a real time. While the hardware dependency is there, deep learning models, if you will train properly, then you must require the GPUs in your laptops, in your machines, or you require a supercomputing facility to train your deep learning models. While on the other hand, machine learning is a very low cost solution which can be runnable on your desktop, on your normal laptops, on your general CPU cards. Then we will move towards the hype of the reality. Like one of the most known person of the deep learning, Andrew Neff, he has talked about like I have worked all my life in machine learning, and I have never seen one algorithm knocks over benchmarks like deep learning. So in a machine learning, he is telling that there is no such algorithm where we can get it will come over the deep learning model. While some other more renowned persons like Geoffrey Hinton from the Google, Dilip George from the Vicarious co-founders, they have given a lot of such comments or the quotes that okay, yes, this deep learning is really important in a daily use because it is providing a much better accuracies, while internal architecture is totally black box, but we are able to get our task done without taking care of lot of efforts. So we will talk about this. So what the deep learning is all about? We have the parts of machine learning field where we can get the learning of our data representations in the form of the patterns. It utilizes the learning algorithms that drive meaning out of data by using a hierarchy of multiple layers. So we have a network of neural network of multiple layers, and using these layers we can get the output. So, guys, one important thing which we want to discuss that this AI system, which is having a power of ML plus some other aspects, plus which is including a deep neural network, the base of all these systems is our neural architecture. So if we will talk about the neural architecture, then we come directly on the neural network. That okay, neural network is the base for to design any type of deep architectures. Okay, so the power of neural network is really important while designing algorithm. Either you want to work on the machine learning or you want to work on deep learning. So what is this neural networks? So let's start. I will take you to this architecture, feature engineering, which is quite take a lot of time to consume to extract the features, while deep learning you simply pass the algorithms. And the second point, deep learning is dependent on neural network. So is there any neural networks which are available to us, and or what type of neural networks is available in the market which becomes the benchmark nowadays to work on? So if you will check out, we have the hierarchies, like every layer by layer, we are moving towards the our output, and every layer is going to transform your input to some desired output. Okay. So now let's start with the one more important phase of the neural network family. Okay. So I think I have taken this part other means separate from my machine learning because we want to check it out that how many type of neural networks these researchers have proposed in a market, and now they become a benchmark. Okay, so what type of these are? If you are you able to see these markings on your left hand panel? Backfed input cell, input, noisy input, hidden, probabilistic, spiking, output cell, match input output cell, recurrent, memory cell. Okay. So these are the basic building blocks of any neural network. Okay. So I am taking you to the journey of this neural network. The very first level of the neural network is about the perceptron, feed forward, and the radial basis network RBF. Okay, so what is happening in a perceptron model? We have the input cell, and orange one is the output cell. two input and a output. That's it. While in the perceptron model, we have the input and output, and in between input and output, we have a one hidden cell, which is going to help us to compute a more complex problem. Fine. Then we have the radial basis network with the same architecture as the feed forward, but the activation function is a non-linear radial basis activation function is going to be used in place of the linear function, and we can get a new network which is called the radial basis network. After that, we have heard about the back propagation network as well. Now, leaving that behind, now check it out how many different type of or the authors have used these different components to make a large collection of neural networks. Like a first, deep feed forward. Why it is called deep? Because we have introduced more number of hidden layers in our network. So same input output, but with a count of hidden layers is increases. We have the recurrent neural network. If you will check it out, now the shape of these hidden layers is changed from green to blue, and this blue is your recurrent cells. If you will check it out at the top, we have the connection like a same input or the output is fed to the same neuron again. So this is a recursion type of thing is happening in this type of network. So just changing the internal hidden layer with the recurrent layer, we are able to handle the problems of the time series data now. We have the long short-term memory LSTM based models. If you will check out the difference between RNN and LSTM, then in RNN you have a single recurrent cell, but no memory cell is associated, while in a LSTM with a recurrent you also have a memory cell. So one circle, a blue circle with a recurrent unit is called a memory cell. It also has a memory to hold the present state, and then it will compute the next state. So it will check it out again. It is going to be used for the time series data analysis. Then we have the gated recurrent unit. Gated recurrent unit means the probabilistic different memory cells. Not the all the memories are of same shape, same size, same dimension, but we can have a gated part that somewhere it will store, somewhere it will pass on, and that's how you are able to extract more complex problems. You can drop some irrelevant information from your network, and that's how a new network family is being generated called a gated recurrent unit. Then beyond this, we have a autoencoders family, which is mainly used for the segmentation type of problems or the clustering problems, where we have the orange input match input output cell. Okay, so this encoder is actually used to match that whatever you have passed after becoming a bottleneck, you need a one skip connection from the input layer to your bottleneck, and that's is this autoencoder family match input output cell, which can actually check that whatever you have given is actually what you are getting or not. So this is the autoencoder family, and if you will include a probabilistic hidden in this autoencoder family rather than a simple hidden unit probabilistic value, then what you are getting, you are converted a model autoencoder into a variational autoencoder. Variation because you are getting a variation in the form of the probability distributions. So once this probability distribution is associated with my segmentation, then I can get I am able to solve some those problems where we have the fuzziness associated with us or in a segmentation. Then we have the denoising autoencoder, where we have the noisy input cells. So in case we have the noisy input cells, then we can use this type of denoising autoencoders, because in an input cell we have a noisy type of filters available which can get rid of these noise parameters, and then we can move towards our proper segmented output. This is actually used in the medical type of problems, where we can work on ultrasound segmentations, we can work on heart arteries, like these problems, medical problems. This denoising autoencoder is mostly used. Then we have the sparse autoencoder where the neurons count of your hidden layers is much or twice the number of input layers and the output layers, and this will give you a more complex nature, because if you will check it out, the degree of all these input and output, it's become same, all the degree counts, but these networks, these count, the number of weights will become more, and the complexity or the computations will increase, and you can get a more detailed parameter values over this sparse networks. After then, we come towards the Markov chain probabilistic model, where we can use a unsupervised nature, where all the input cells, where all the probable cells are in a form of probabilities, and all are interconnected in just like a complete graph we have. Then we have a Hofield network where backfed input cells are there. That means input is not always going in a forward direction. We can also take that input and feed back again to compute that, okay, in a one pass, two pass, what can we change the nature? Can we get some more relevant features? It is something like in a short we will check it out. Then जैसे गन्ने का जूस निकालते हैं, एक बार फीड किया, जो निकला उसे वापस दे दिया, फिर कुछ और निकल कर आएगा. So just like this, we can use the data again and again, so that till that once we are keep on getting some new features, we keep on feed it into the network. Then we have the Boltzmann machine. We have the restricted Boltzmann machine used for probabilistic type of networks. Again, probability, totally unsupervised probability, time series, stock predictions, and NAV, finding a NAV value of the stock. Like this type of problems, we have used these type of neural network architectures. Beyond this, we have the deep belief network, a very, very complex network which is considered in past because it has the backfed input, it has the probabilistic hidden cell, it has the normal hidden cells, and this repetition of probabilistic and normal is repeated several times, and at the output we have the input output matching. So it is totally based on the belief that whatever we are feeding, whatever we are extracting, we are getting the relevant information, and based on the probabilities that, okay, our probability association is keep on increasing as we move on the training data a lot. Then we have the deep convolutional network, DCN. Deep convolutional network. What the convolution means, from here onwards, actually the deep learning is started in a market. Till beyond this, we are actually working on the different families of neural network. Why we call this a deep convolutional network? Because, or a starting of the deep neural networks, because here whatever the operations you will do intermediately with the weights is actually done by the convolutional operator or the filter. So as I shown you earlier in the slides, that we can extract the edges, then we can combine these edges. So yes, we can do this, but how we can do this in a deep networks? That is a part of my convolutions. So we can use some kernels over here, normal kernels, 3 by 3 kernel, 2 by 2 kernel, and basis on these kernels, my convolutions are performed on my input image. Once the input image is convoluted, its pixel value is increased in case if we will use a 1 cross 1 filter, okay, with some high value. Otherwise, all the intermediate pixels, suppose a 3 cross 3 window, so the center point of my 3 cross 3, that pixel is increased by a factor, some factor, and which is it can be done by this convoluted, and multiple convolutions has been done, and at every hidden iteration, your convolution, the size of the neurons, the count of the neurons is in keep on decreasing, so that you can get a type of the slant type of thing, means your dimensions keep on decreasing but the vector length keep on increasing. Okay, and that's how you can get at the last layer when you will do a fully connected, most of us we can get a 1000 dimensional there, a vector which can be helpful to make any predictions in a deep modeling. So we have the deconvolution. Once you will done the convolution, then we will move towards the deconvolution operations, where this again is used in autoencoders family. This is you going to be used in segmentation problems. Then we have a inverse graphics network. This is proposed by the, I think, Google, to hand over their problems associated with a graphical type of thing to generate the new images, like your GAN model is there. So this type of model, including the convolutions, including the probabilities, it can generate, you will pass the text, it can generate the image. Something like nowadays Chat GPT version 4 is doing, or the AI engines are doing. You are passing a text and it can generate you the image based on your text. Then we have a generative GAN models. Then we have a liquid state machines. Then we have a extreme learning ELM machines. Then we have the eco state machines. So the power of ELM and the eco state is almost same. So you can use any of these alternatively. The only the difference is here we have the recurrent units, here we have the simple hidden unit. So in case you are working in time series, then eco state is feasible for you. In case you are working on a static time data set, then ELM is better for you. Then residual Cohen's network, we have the neural tuning machine. The latest machine which is used by in a one, it is being published in recently last year by, I think, the Facebook or some other organization, which can handle the problem of language specifications. So for NLP domains, this neural tuning machine is being developed, a very powerful machine which are actually taking care of most of the language problems, transliteration or the translation type of thing can be done with this neural network family. So these all are the different variants of my neural network or the deep learning, which is actually designed for a specific problem, but yet they are totally independent. You can use in some other domain as well. Based on your applications, you need to choose, you need to select some basic network, and then you will experiment your data, and really you will find the good results on your machines. So the final, once you will done with the modeling part, then you will come towards the result, and this results includes two aspects. Once you are getting a results, then can we visually interpret the results, like images you are getting some segmentation, and you are able to see, okay, that segmented part is okay to me. So what type of interpretation you can get? It's called a qualitative analysis. While we can use a human friendly interpretation, where we have the some automatic annotations will come, where we can have a quantitative analysis, some quantity or the value is there, then we can use that quantitative analysis aspect as well. So now we will move towards the some of the aspects of the work done. So as the domain of study is my medical imaging, so I can take you to the journey whatever I did in a, especially in a machine learning phases. So this is a total research domains in which I have worked on gait abnormalities like a prosthetic joints. We have worked on a microscopic imaging, histopathologies. We have worked on the medical imaging, MRIs, ultrasounds. We have worked on the machine learning, segmentation, and the classification parts. So we will start first these images with respect to segmentation and classification aspects. So just check it out. Once we start the work, I will tell you first problem over the gait abnormality detection, prosthetic. So we will check out that how we can start our problem. So do we really need a very big data? Do we really need a deep model or the simple machine learning complex models, neural network complex models? No. If you will check out this study, this is a human gait, and the human gait is called a way the person walks. Okay, so just by checking the way of walking patterns, we can find whether the person is having some abnormality or not. Okay, so this study is actually being used in a physiotherapy type of thing. So just check it out. Series of rhythm, alternate movements, trunks of limbs, जो हमारे forward propagation में, which is actually is using in forward propagation of gravity. So we will do a first gate initiation. That means a gate cycle. If you will check out this second diagram, so we have a two type of phases in a walking. One is a swing phase, one is a stance phase. So once we will walk, our heel, our foot, our toe will touch on this ground, and at some point of time it will remain in air, and again it will come back on the ground. So what we will do, we will find a gate cycle over there, which includes a period of the time from one heel strike to the next heel strike. So this gap is called a one cycle, gate cycle, and we have the two phases. If you will check it out, then swing, 40% of the time our foot is remain in a swing phase, while stance is no 60% time we will remain in a instance phase. And here we have the diagram of the instance and swing. So what this study includes, actually the problem is we have worked in this problem with the Bhagwan Mahavir Viklang Seva Samiti, where the patient is having the prosthetic joints. That means in an accident they have lost their some limbs like a foot or a leg. So once their body part is missing the prosthetic, then they have used some prosthetic. Doctor mostly recommends prosthetic joints, and that is a really costly cost solution, and it is the most feasible. As a human, we always rely हमें imported चाहिए, we need a imported joints. And then what we go towards, we will go towards the 3R15, 3R16, which is a German based product. So this German based product is really costly, and and our the motive of our studies, this really help us to identify some gap, or this really prosthetic joints German base is really helpful to the community or not. We also have some local solutions over there, like this local solution is in a form of a Jaipur knee, which is developed by the Stanford University and Bhagwan Mahavir Viklang Seva Samiti Jaipur. So we these two organizations, they have collaborated, and Jaipur has created their low cost solution, which is known as the Jaipur foot or a Jaipur knee. So the objective is study to check it out whether this Jaipur knee is feasible or not to the patients who are actually lost their limbs. So what we will do, we have taken the kinematics and kinetics data. Kinematics, which describe the movement patterns without regard of the force involved in producing the movement. So what we have done, we have not taken care of any force. We have just take care of the patients. Okay, you will walk, and we have noted down the time period, what time period the patient is taking to move from one place to another place. While we will use the kinetics as well, where we have placed some sensors on the foots. Like if you will check it out in this photo, you will find some sensors are placed over this thighs, over this lower back, and this is a treadmill type of thing, which is called a force plate. So we can extract some numeric data from these sensors. We have fetched these values. So this whole study, if you will check out, so we have done this whole study through kinematics and kinetics. We have a collaboration between VANET, JP, IIT Dhanbad, Bhagwan Mahavir Viklang Seva Committee, and then we have a subjects which has taken from a 0 to 16 years and 5 to 27 years with the prosthetic joints. So to evaluate the performance with this low cost Jaipur prosthetic joint and compare with German based 3R15 product, and what we did, we have created a one three-dimensional environment. We have created a one lab setup. In that lab, we have a different cameras at the different locations and the orientations. We have the force plates, we have the sensors. So we have captured the kinematics data with the help of these cameras. We have checked all the kinetics data with the help of sensors. So using this collective information, we have used this to find that whether first initially the patient has wear the 3R15 prosthetic joint, and we have we told the patients that okay, you will move comfortably, there is no one in a room, okay, you will move comfortably. Patient has moved from one place to another place, and his or her data is extracted by the sensors and the motion cameras. Same way, same patient, same distance, average conditions remain same. Only the prosthetic joint is replaced with the 3D, sorry, this 3R15 to Jaipurni, and again the patient has walked. So we have repeated this experiment 2 or 3 times per patient, and we get a very good data set. And on the basis of those analysis, because see, if this is a time series data, per second we are calculating. So this is the time series data, and no imaging we have used the some numeric values. So by definition, what we say, we are not in a state to use any machine learning or a deep learning classifier or the problems. So what we will do, you use the logistic regressions, use the regression analysis, and find the solution whether which joint is having a better performance. So we did this part. This person is saying time, percentage, cycle, lower instance. We have identified these 3 parameters using the data set. First, the step length, distance between the heel contact point of one foot and that of the other. So that when a person walks, we have captured this thing using the motion cameras. Stride length, distance between the successive heel contact points of the same foot. Normally, stride length is a twice of the step length. So, in once you will walk comfortably, this parameters remains the same. Okay, in case you have any abnormality in the leg of the patient, okay, so you are able to see the differentiation in between these values: stride length, step length, and the cadence is the rate at which the person walks. Express steps per minute. Cadence average is 100 to 115 steps per minute. So in case we will identify that okay, these parameters are not going in a normal way, then there must be some abnormality, and this thing is actually used by the physiotherapist. Okay, but our motive is to identify the performance of our Japanese. So we have taken all these 3 kinematics data, sensor data, kinetics data in an integer form, and we have done this analysis. So what after doing the detailed analysis with the regressions, and then what we concluded at the last, step length using Jaipur knee is more towards normal range as comparative to 3R15. That means once the patient is wearing these two joints, 3R15 and Jaipur knee, the patient is much and much more comfortable in walking as comparative to Jaipur, oh, sorry, this German based product. Stride length. Ratio of both legs stride length are found relevant for patients wearing Jaipur foot, which is better than 3R15. Again, stride length is improved with the Jaipur knee, Jaipur foot. Strap length is included, which is really improved. And last, the cadence. And what is, if you will check it out, average cadence for Jaipur foot is 90 to 105, and 3R15 80 to 95. Okay, so if you will check out the cadence, then Jaipur knee or Jaipur foot is really giving you a very good results, and it is a very low cost solution product developed by our India. Okay, and once we have shown these results to the research institutions like the Army R&R Hospital, New Delhi. We have shown these results to the various physiotherapists, various these research laboratories, those who are working in this domain, and we found really that the performance of this Jaipur knee is far better than 3R15. Also, it is a very low cost effective solutions, and it is providing a much satisfactory results to the patients who are actually wearing this. So the impact of this study, what the impact has done, we have taken these results, which is actually published in, if you will check it out, published in Journal of Medical Systems in 2019. So this impact, once we have taken this impact to the community, research community, to product in a form of the product to the market, commercial, then these orthopedic surgeons from government hospitals, Army R&R hospitals, and other research organizations, they are very much satisfied about this steady, and now they are recommending the Jaipur prosthetic joints over German products. And this has really created a revolution. And for the last 2 years, we got the results that earlier, before 2019, in case the whatever the order of okay, so fine. So now we will move towards some imaging related work. So what we did in the imaging. So just check it out. As I have worked on the imaging, MRI versus CT. So depending on the type of this abnormality, the choice of data, whether MRI or CT, is really changed. So, like the tendons and ligaments, if we have a point of interest in this ligaments part, then definitely MRI shows a very good results in a form of data, while CT is not a best choice. Brain hemorrhages, CT is the most appropriate one, while MRI is not having that information, good information. Brain tumors, again, MRI is good. Bone structures, CT. Organs injury, CT. Bones, broken bones, beyond the X-rays, we have the CT, which can give you a more detailed structure. Spinal cord problems, we can use this MRI. So these are the some of the areas, point of interest, where we have worked in a past, and that's how we have done a choice that which imaging modality is suitable for us. So fine, now we are moving towards our ML models. The very first part, segmentation. So before that, we have used the k-means, fuzzy c-means algorithm only for the segmentation perspective. But if you will check out that, can we make some new algorithm in the market? Can we bring some new algorithm? Then I have worked earlier, means a long back. I worked on this clustering part, hierarchical. We have used a disjoint tree based clustering. So we have the idea of forest, we have the idea of graph theory, we have the idea of for trees, how to form trees. So we have done the same part. We have used a disjoint tree based clustering and merging, and it is going to be used for extracting the brain tumors, to segment the brain tumors from the MRIs. We have done this approach using a graph theoretic approach. Then we have generated the disjoint trees from the image matrix. Each tree will represent us one cluster, and then merging of the trees based of the nearest approach. So many core concepts is going to use to merge up in this one algorithm, and which can result in a generation of some new algorithm in a clustering domain. So if you will check out, let us suppose this matrix is there, which is having some values, and on the zeros it will create all the trees, and like the how it will create different trees, it will form a forest. Then these forest is going to be merged up one by one using a graph theoretic approach. That how you can work nearest approaches based. So lower dimensions trees will keep on merging to one side, higher dimensions will keep on going to merge side, and that's how keep we can get a numerous number of trees which will go. And at the point of time, we can came up with a one such solution where all these trees will not going to merge up to the one level, but till at the point where all the trees will have a equidistance parts, and on that part we can get some results like in this form, like a proposed algorithm results. We have a three different type of imagings, MRI images for the brain tumor. And if you will check out, this is a results which we got over here at the k is equal to 4, means the 4 number of clusters. So the algorithm stops when we have the 4 forest. In the forest we can, all the trees is going to be merged, and we are resulted in the 4 different trees only. Then it will stop, and that's how you are able to see some images with respect to the imaging modalities, like a T1 weighted, ET1 weighted, and this one is T2 flare. So we are getting a very good results, seems good results, but visually it is okay. But what about the quantitative wise? We haven't checked right now. We haven't checked this as a quantitative. Qualitative wise, it's okay. Quality wise, it's looking good. We have done a very good segmentation part. So what we will do, then I will show you the quantitative analysis of this. Then We have extended this algorithm. Okay, so it's a small work which is published in 2014 Springer. So after this, we have done use the probabilistic modeling theory, probabilistic models. So we have came up with a solution. Okay, rather than going towards the nearest neighbors, let's start fetching the find the disjoint set. Then we have to link two disjoint clusters using the probability mutual information. So we have used this PMI to merge these trees, and once all these trees is going to be merged and we come up with the solution, then we are able to get the more informative clusters. So like this, suppose in this graph we have two nodes 0 and 1 having a some probabilistic information like 0, 2, 0, 8, and this is going to be merged using a joint probabilities. Then we are came up with an edge to join these two nodes with some value 0.0016. This is one such example. So like this, we keep on adding these two nodes, and we came up with a one single node which is called a 0, 1 cluster with some different probability value now, which is came up using a this disjoint clustering approach. So once we are done this type of approach, we have proposed one algorithm over there, and we are resulted finally with the updated set having a cluster which is also called the cluster set. And over this cluster set, so what information we can get once we are replaced with the nearest approach with the probability based approach. So if you will check out, then you will find a very good visualization results. Now if you will check out in earlier results, we are not in a state where we can mark these boundaries, head boundaries. But now if you will check out this in PMI, using a PMI, you are getting a very clear cut pictures. We are getting a bone structure, light bone. See in a B part, very light bone we have at the top, and in a E part we are getting this segmented part as well. So this is not only enhancing the image, it is also extracting the relevant bones, nearby tissues. It is taking care of many such parameters, and the visualization is also important to us. So visualization wise, the algorithm is working very fine. So what about, okay, qualitative wise it's okay, but what about quantitative wise? So if you will compare the qualitative analysis, we have taken the input image, Otsu method, we have done a region growing approach, morphological, K means, fuzzy C means. These all are the state of art methods which are available in our machine learning community, existing algorithms. Then we have used our proposed approach. So I haven't included this hybrid. This is a very common approach. So I have talked about this hierarchical and the hierarchical PMI. So if you will compare the results, PMI results with all these results in a first row, then you will find that, okay, yes, tumor is there and it is expected. Beyond the tumor, we are able to identify the small light minute patterns as well of the brain. Okay, and this information is available throughout all the three exact images of my brain tumors. So once we are done with this new clustering approach, now we will move towards the quantitative wise. Is our algorithm is better? We have taken two indexes, DB index and the Dunn index, and we have calculated with the traditional state of art method with our proposed approaches. So you will find that, okay, this PMI is really performing best among all the cases. Okay, among all the cases, PMI is really performing the best, and this algorithm is very good in identifying the segmentation with the enhancement. Okay, so this can be used in a segmentation and image enhancement. Okay, next, our phase is a feature extraction phase. So in a feature extraction, what we will do? We will extract some relevant features. So traditional method is GLCM. GLCM, gray level Cochrane's matrix. There we have the four different orientations theta. So we have designed on a similar theme. We have designed a one new different feature extraction algorithm which can replace GLCM type of features, traditional like a counting level occurrence matrix, which can be used for feature extraction in MR. Again, the same theta value we have used as GLCM. That's if we cannot use the same properties, then we cannot compare the two algorithms. Okay, so how this clone actually works? So this is an algorithm. So let's see the description. Suppose we have a image, brain image. We extracted some random pixels, are these random pixels. Then we have identified the maximum values, gray level, diagonals, and the rows. Based on these, we have the four orientations. We are designed with the four matrices over this. One is a 7 cross 4 diagonal versus gray level, and the second one is a 4 cross 4 rows versus the maximum grade level, and then we can design a horizontal, vertical, right diagonal, and left diagonal. Means the four different orientations of these GLCM type of thing. So using these values, we have identified set of 5 class of brain tumors, T2 weighted post contrast images, 150 images of data set, small data set. That's why we are going to use only the machine learning, and all these images are the real patient images which has been taken by me only from the SMS Medical College Jaipur. Okay, so my SMS Medical College Jaipur has associated with this project. We have designed this algorithm. We have extracted some 8 features, just like the traditional GLCM has done, and then we have compared that. Okay, these 8 features from GLCM and these 8 features from my matrix, clone matrix, then which will perform better? Two classifiers is going to be used here, KNN and neural network. Okay, so if you will compare the results, then we are able to find that our proposed clone algorithm with the KNN k is equal to 7 and the neural network is really performing best in all the 5 type of classes. That means this proposed algorithm clone is actually providing a more informative features as we have done in the past with the GLCM based features. Okay, so more information, more informative results we can extract from code and clone, and this is my first contribution in the first phase of machine learning, which is called my feature extraction. So new algorithm we have designed in the feature extraction phase. Next feature extraction algorithm which we did is a TOM, texture occurrence matrix, in a texture domain. Okay, so how we can extract the textures? So we have designed a 9 filters to extract the textures over there. So these 9 textures are going to be used to extract the textures from any input image. So this is a block diagram, complete block diagram of that proposed approach. We will use the filters, we will use the filtered image, find the textured image, then we will create a one common matrix, TOM, texture occurrence matrix. So earlier it was GLCM, then we have extended that to clone, and then we have extended to TOM. So once the TOM is there, we have the features, spatial and spectral. We created a new feature extraction approaches using these approaches, and then we have compared the predictions. So how this really works? We have some segmented data which we extracted from our proposed algorithm. Then we have over all the size of the image, we apply all the filters. We extract all the filters where we have the filter values. We find the textures. These textures is converted into the matrix. That's how we can create a one final texture index matrix. We will create a texture occurrence. One is low pass, one is high pass. We will create a texture occurrence matrix. This texture occurrence matrix is created, and once it is created, we can get our upper and lower triangular matrices over these values. Once it is done over this extracted value, we are faced a different probabilistic approach, 9 features, index approach, 8 features, PCA, 9 features, Gabor with the two different theta values, 40 features, total 66. So once these 66 features are with me, I have experimented this with previous algorithms, GLCM and run length, traditional algorithm with the neural network and KNN classifiers, and what you are supposed to see that okay, yes, this texture is providing a mean accuracy of 91, while other algorithms is of 85 and 79, and while with the neural network, as the power of neural network is really high, then we are able to get up to the 93% average accuracy. So why should I go for a deep learning once I have my own algorithm which is giving me a 93% accuracy in machine learning domain? So we have done this part, feature extraction. Move towards the classifier. We have the classifiers like the KNN, we have the classifier, decision tree, SVM. So what I did, is there any doubt, any question? Yes, I think no question is there. Okay, got it. So we have designed one classifier, our own classifier in this community, machine learning community, which is called the AVNM, a voting based novel mathematical rule for image classification. So here, what we did, I will take you directly to the algorithm. Is it, if you are interested in this algorithm, then it is being published in 2016. Voting based novel in computer methods and programming biomedicine journal Elsevier. So you will check it out, this algorithm, and you will see a detailed description of this. I will take you directly to the approach. So this is a graphical representation. Like we have a one sample space, we have a different type of samples, classes are there, and we have some query sample which exist in this sample space. Okay, so the task is this sample space S is repeatedly, iteratively, it's keep on decreasing up till this S dash. Okay, and till this S dash will reach, then our algorithm will stop such that no more decomposition is possible for this classifier. And for doing this, we have a mathematical rule. If you will check it out, the algorithm, you will find out that these all are the features that we have to find some weighted sums, we have to find the distance, we have to set the thresholds, and then we have to take some weighted computing, the weighted average, and then how we can go towards this final step. Okay, so once this class is neighbor is been done, our class assignment is going to start applying this model. So the main thing is, okay, then how this classifier is workable is okay, but how this classifier is comparable. So we can compare this classifier with the KNN because it is also a multi-class classifier. And in a KNN, one problem is with your selection of number of nearest neighbors. Okay, so we cannot say that for every problem k is equal to 3, 5, or 1 is will give you the best answer. So there can be some other value of k as well which can give you the best answer. So this algorithm, this proposed approach are able to find the best possible k value dynamically without any human intervention, and can give you the best results as comparative to KNN. So in this whole experimentation, we have taken two data sets, one from the UCI with a large number of attributes, different, and we have our own 5 classes of tumor samples, and now we have increased the data set size from 30 per images to multiple images per class. Once we have compared this with the KNN, because since our approach is of nearest neighbor based approach, then we can only compare about with the nearest neighbor. So with nearest neighbor KNN and its variants WKNN, UWKNN, DWKNN, and this is our proposed AVNM. So we have find the error percentage with respect to K. So you will find it out that okay, yes, for every data set here, every data set, our algorithm is giving a different values of k, and on these values of k we are getting the minimum distance, and this whole computation is totally dynamic, no human intervention. You have to simply call the algorithm and it will give you the final output that okay, these are the number of nearest neighbors is required and this is your minimum error rate which you can get. Same with our tumor data set, we are able to get the very least amount of error percentages as comparative to other KNN based algorithms. So the once we are done, we have to prove our classifier with the statistics. Like, is there a statistical validation exist? Then okay, yes, we apply the Neckmeyer test to prove that our classifier is really perfect. performing well. And this Nackner test is mean to compare the performance of two classifiers. Okay, so this is a well-known class measure to compare the classifier performance. So we have applied this Nackner test with the formula, and what we have identified with respect to different AVNM versus KNN, WN, KNN, UW and DW. So these are the values which we got over here, and all the values is actually beyond that level degree of freedom, and we are able to claim it that okay, yes, our classifier is statistically validated. Okay, so these are the phases in which we have worked on in a machine learning environment. Feature extraction, we propose two algorithms. Feature selection, we have also proposed one algorithm, but we haven't included that part. Classifier, we have done one, designed our own classifier. Same way in a segmentation, we have done two algorithms in a segmentation. So that's how we can say that yes, in a machine learning environment is also research oriented, not is like that only deep learning is really helpful. So in case you are able to design anything from the scratch, then definitely you can get a better publication, you can get a better result in a machine learning community as well. So at the last, I will take you, I think the time is up. Okay, so I will take you a quick journey on what deep learning models we have done on which problems. So first is a histology, breast cancers identifications we have done. So we have proposed this architecture, deep proposed deep model architecture, and here we have the this our own designed architecture. This is not the existing ones. So we haven't used any existing architecture in any of our work. Just for comparison, we have done. Otherwise, we have created our own architectures to solve any medical related problems. So we have designed this our own deep architectures, and that's how this is a layer by layer description that which layer is for what convolution size, which filter, where what can be the hyperparameters associated. And once we are done what we have done, we are able to get this results. So this DenseNet 169 is the best available network on this data set when we compare multiple existing models. So we have only compared with the DenseNet because experimentally we have compared 10 models, and out of those 10, DenseNet provides us the best results. So once we have divided this, compare this dense 169 with our proposed model, and we are able to see that okay, yes, our accuracy is really good. Okay, and this work has been done as a part of a one Kaggle competition. Okay, so this work has been done one of the UG student. He is associated with me, and we both have done this work. So in this test set on a Kaggle, we have claim it the accuracy we got, I think the third rank we got over there in the Kaggle competition. So we got this public score and the private scores, which is very high. See, in a split of a 90-10, we are getting almost 98.21% accurate results of our model. Okay, this is a proposed architecture with other deep models except the DenseNet. Okay, with the precision recall measures. So you will find that okay, yes, yeah, accuracy is really high. Precision recall F measure is getting almost 98% with our proposed model. So this model is now accepted in. I think we haven't mentioned the name. Okay, yeah, it is published in Neural Computing and Applications. The second one is the visualization. So we have extended this proposed model with some more mathematical constraints, gradients. So we use these gradients vectors that okay, at a which place we are getting the most gradients. So for that we have used these last two layers data, and we have used the gradient information, and then we have mapped the attention map, and that's how we are able to get the heat maps of my data. If you will check out non-tumor samples, we are getting no heat map. Gradient is almost same in every layer part in the last layer, but in the tumor samples 99.98 accuracy, 99% accurate results we are getting with the heat maps. So just with the play of these last layer work, we are able to get the very good highlighted results or the cells, which cells are having a maximum abnormality and up to which place it is distributed. Then on an ultrasound, fetus head localization, we have done this work. Traditional inputs, if you will see input output, not a very good results we got with that k-means, FCM. We apply the contours as well, so we are not getting a good result. Then we have start towards our deep models. So we propose a one model, mask pixel model. It is proposed, it is been now published in a Elsevier. So this model, once we have started this model, we have designed the layered architecture, so it becomes a very complex model because ultrasound images are really complex ones. We are not able to see the annotation, we are not able to see the internal organs, so we required a very high computationally efficient model to do this. So this is a model which we have designed. So we have some other parts. Okay, we have phase by phase, we have some skip connections, we have the concatenations, and that's how we are able to design these contours. Okay, so if you will just check it out, original image, and this is our fetus detection part. So in the pregnancy, in the first trimesters, second trimester, we are able to identify the fetus exactly, and we can able to find the growth rate that fetus is growing up to which model. If you will check out the ground truth, which what I have and what we get, the comparison of these two detections, we are getting almost 97.6% accurate results from our modeling point of view. Other, in a COVID time, we have done this differentiation, pneumonia versus COVID-19 infection with our proposed model earlier with a grad camp. So we want to test whether our model is actually integrable or not with other applications. So from a histopathology to COVID-19, we are able to find, yes, now model is really extendable. It is become a generic after learning on multiple data sets, and we are able to find that okay, pneumonia is there, and we are able to find that okay, COVID-19 infection, which part of the lungs is having a more cavities type of things. So we are able to differentiate between the pneumonia and the COVID-19 with our proposed deep models. So we have some futuristic applications like the diagnosis, prognosis, patients atlas constructions, career advice. If any one of you want to work on a medical imaging, then we have some research challenges you can find in a biomedical image analysis, MICI, ISBI, SPY medical imaging. We have the toolboxes to start on like a Python, Mevis Lab, Biodigital, CUDA, Library for NVIDIA. So you can find all these things. Okay, so we have the medical imaging open data sets with us, which are available to you, and you can find a lot of data sets. And from where to read about the medical image analysis, we have the general readings, we have the specialist literatures. You can find a very good papers of medical imaging. Conferences are also there. These all are the A star conferences. You can find your works, efficient works over there as well. And thank you for